Before the moon landing, before satellites, and long before reusable rockets, there was the V2. It wasn't just the first rocket to touch the edge of space. It was a bold declaration that humanity could break the bonds of Earth. Born in the chaos of World War II, the V2 rocket was a technological marvel far ahead of its time. Originally conceived as a weapon, its underlying science became the foundation for modern space exploration. It was the first human-made object to reach outer space, crossing the Kármán line and proving that space travel wasn't just a dream. But reaching that milestone was no easy feat. The V2 project was plagued with enormous technical challenges. Engineers were treading into uncharted territory. Rockets of this size had never flown before, and the problems they faced were as unforgiving as gravity itself. One of the biggest issues? Fuel combustion stability. The V2 used a liquid fuel propulsion system combining ethanol and liquid oxygen. But early tests were disastrous. The engines exploded more often than they fired. Engineers discovered that mixing and injecting the fuel at high speed created turbulence that caused the engine to self-destruct. Their solution? The development of a combustion chamber with regenerative cooling, circulating cold fuel around the chamber walls before combustion to prevent overheating. This was revolutionary. Today, that same principle is used in modern rocket engines like the SpaceX Merlin and NASA's 25 rupees. Then came the problem of guidance and control. The V2 was the first long-range missile with an internal guidance system. But without modern computers, engineers relied on gyroscopes and analog electromechanical devices to keep it stable in flight. It took endless trial and error to ensure the rocket could stay on course. But that crude system laid the groundwork for today's inertial navigation systems, the very tech that helps guide satellites, intercontinental missiles, and even your smartphone's GPS. The materials used were another headache. At high altitudes and supersonic speeds, traditional materials would crack, warp, or burn. Engineers experimented with new alloys and heat-resistant designs to keep the structure intact during flight. These lessons shaped the future of aerospace metallurgy, influencing everything from the Apollo missions to modern space capsules. Perhaps the most unsung but critical challenge was the turbopump. In order to feed massive amounts of fuel into the engine, they had to invent a compact, high-speed pump that could survive extreme heat and pressure. The result was one of the first high-performance turbopumps, a piece of engineering still essential in all orbital-class rockets today. And through it all, there were no computers. No digital models. Engineers solved these problems with slide rules, hand-drawn blueprints, and relentless field testing. Every launch that failed taught them something new. Every explosion led to a redesign. Every mistake became a stepping stone to success. And eventually, it worked. The V2 launched successfully and reached space. Though it began as a weapon, its technological triumph became a pivotal chapter in aerospace history. If you're enjoying this journey into the early days of space innovation, now's a great time to like this video and subscribe to the channel. It helps us bring more untold stories of science and engineering to curious minds like yours. When the war ended, so did the era of secrecy. The world's leading powers realized the V2 wasn't just a weapon, it was a treasure map to the future. And both the United States and the Soviet Union raced to claim it. In a covert mission known as Operation Paperclip, the United States brought over more than 1,600 German scientists and engineers, including Wernher von Braun and much of his V2 team. They were taken to the US not as prisoners, but as strategic assets. There, they began developing America's first ballistic missiles and eventually, NASA's Saturn V, the rocket that took us to the moon. Meanwhile, the Soviet Union, not to be outdone, scoured Eastern Europe and captured their own share of V-2 components, launch sites, and German engineers. They reverse-engineered the rocket, launching the R-1, a near-identical copy of the V-2. This gave rise to the Soviet space program and ultimately led to Sputnik, the world's first satellite, and Yuri Gagarin, the first human in space. The V-2, built in wartime darkness, became the blueprint for both superpowers' journey into space. Its technology seeded a new global competition, not for territory, but for the stars. The legacy of the V-2 echoes through every modern launch. From Falcon 9 boosters landing on drone ships to Artemis rockets preparing to return us to the moon, the foundational tech, liquid fuel combustion, turbopumps, guidance systems, can all be traced back to that first leap made in the 1940s. Today, as we build toward Mars, space stations, and deep space missions, the vision that started with the V-2 is evolving, but never forgotten. So, what do you think the next great leap will be? Let us know in the comments below. And if this story inspired you, share this video with someone who believes in the power of imagination, determination, and science to shape the future.